So just to review the electric field of a point charge, let's start with. The electric field in general for any collection of charges with a net electric force is equal to the electric force per unit charge, or the electric force on a test charge Q is, if the electric force on test charge Q is F net electric, then we just divide out that test charge to find the field. And that tells us that the electric field due to a point charge is equal to Kq, if the electric force was KQ1, Q2 over R squared, then the electric field due to a charge Q1 is just KQ1 over R squared. So if we have a positive charge Q1 at a distance R away, the electric field at that point is KQ1 over R squared. And it's in the radial direction. It's away from a plus charge and towards a minus charge. So that's what we discussed. And then we discussed the electric field map in general. We can draw an electric field map. So I'm just going to change the color here and just say we got field lines that emanate away from plus charges and towards minus charges. If I had a minus charge, the arrows would be in the other direction. So let's do that. So that's the electric field of a minus charge. And we conclude from our discussion of electric fields that there are three important points about electric field mapping. Fields start on plus charges and end on minus charges. What that means is if you only have plus charges, then the arrows just all go away to infinity. Or if you only have minus charges, the arrows all come in from infinity. But if they're both plus and minus charges, and we'll do this in a little bit, but let's just foreshadow, then they're going to start on pluses and end on minuses. So let's say these two were on the same page, right? They're going to start on pluses and end on minuses, and we get slightly more complex fields. That's actually called a dipole when you got a plus and a minus like that. But anyway, electric fields start on pluses and end on minuses. That the relative density of the field lines indicate the relative magnitude of the field, meaning that when you're closer in to the charge and the field lines are closer together, the field is stronger. When you're farther out, the field lines are farther apart, right? They're farther apart, then the field is smaller. It's not proportional to the density of the field lines, but it just indicates as they get farther apart, the field gets smaller. As they get closer together, the field gets bigger. As they get closer together, the field gets bigger. They get farther apart, the field gets smaller. Then the third thing we discussed, which I didn't leave myself room to run on the page, is that field lines don't cross. And the reason why field lines don't cross is because if they did, that would indicate two different fields. They were pointing in different directions, and the net field is just the sum of them. That's why I was struggling with the net here. This is the net force per unit charge. So it's just the net field. So because we would add together all the fields at a point, then the field lines don't cross. And actually, I should say a little bit more about that, right? Because we have written down the electric field for a point charge, right? The electric field for a point charge, Q, is just KQ over R squared in the radial direction. What if we have a collection of point charges, right? If we have a collection of point charges, the net electric field is simply the electric field due to each of the individual point charges, E1 plus E2 plus E3, no matter how many point charges we have. So you just add up the net field, or it is the net force, and it's the net electric force, not the net total force, but the net electric force per unit charge. Right, that's another way of looking at it. So there's a couple ways to look at that net field. So what's important, this is really important to note, is that the first equation I have here, this is the field of a point charge. It's a special case. But the other two equations I have here are not special cases. It's in general that the net field in any region, this is a general equation, is the sum of all the individual fields built up from point charges or collections of charges. And then this is really just the same equation. It just says that the net field is the net electric force at any point divided by the test charge. These are general equations which apply to any field distribution, any charge distribution, any field. And the first one is a special case of a point charge. So what do I mean by that? So for instance, if I had, whoops, I keep drawing the wrong color. If I had a bunch of charges, charge 1, charge 2, charge 3, charge 4, charge 5, and I want to know what is the field at a point P. This is just a point P in space, right? So we can call this charge 1, and this charge 2, and this charge 3, and this charge 4, and this charge 5. Charge 1 has a field of KQ1 over R1 squared in that direction, right? Where R1 is this distance here, R1. Charge 2 has a field pointing in that direction of, because I'm just tracing that line, KQ2 over R2 squared in the, KQ2 over R2 squared in the direction indicated, so on and so forth. Charge 3 has a field in that direction, charge 4 has a field in that direction, charge 5 has a field in that direction. The net field is just the sum of all those fields, but it's a vector sum. It's not trivial, but it's just the vector sum of all those point charges. Or if somehow we knew what the net force that those 5 charges exerted on a charge Q at point P, then if we knew the net force, we could just take that and divide out the test charge Q in order to find the net field at that point. So that's how to deal with collections of charges. We just have to add up the fields or add up the forces. So let's do an example. Let's say that we have, instead of a single charge, so let's say we have a dipole. A dipole is 2 charges of equal charge but opposite sign. So let's say we have a plus Q and a minus Q. So a plus Q and a minus Q, and they're meant to be, spherical charges or point charges. And let's say that plus Q and minus Q are separated by a distance d. This is called a dipole. A dipole is, again, 2 charges, a plus and a minus, equal charge. So it's a net charge of 0. That's the point, is a net charge of 0. And they're separated by a distance d. This is a very common configuration. Everything is, right, that all your atoms are neutral because they're filled with positive and negative charges. They're actually filled with a bunch of dipoles in most cases, which are equal and opposite charges. Dipole is a common charge configuration in an atom. Okay. It's 1 proton and 1 electron. That's a dipole. Okay, let's ask, what is the force on a charge big Q, a distance of, now I'm asking for force right now, not field, so we're going to start with force and then we'll talk about field. So dipole, force, and field. We'll talk about the field of dipole eventually. That's where we're going. So let's ask, what is the force if, again, the distance separating them was d, for a charge Q, which is r away from their centers. So hopefully you understand that picture. They're separated by a distance d. That's this direction. And r is how far away the big Q is from their centers. So big Q is right here. And big Q is what will be our test charge later. It's the charge we're going to take away. So what is the force on big Q? Well, the force on big Q is, so I'm going to start with the force, so A. So the net electric force on Q is going to be the force of plus Q on Q, the force of plus Q on Q, and we're going to add to it the force of minus Q on Q. So we got to find the net electric force, F, I'll just call it F electric, is equal to F of plus Q on Q plus F of minus Q on Q. And not divided by Q, but just Q on Q. So that it's the sum of those two. So we just take the two pairs of charges. So the force of plus Q, I'll write the word, on Q, is equal to K plus Q, plus little q, times big Q, which doesn't really matter if it's positive or negative, but I guess we're just assuming that we're going to put the sign outside, and the Q's themselves are positive quantities, over r squared. But r squared is the distance between them, which is neither d nor r. What is r squared? Look, the distance between them is this distance here. It's this distance here, right? It's the hypotenuse, which has a short side of d over 2, or that side of d over 2 and that side of r. So the distance between them is the square root of d over 2 squared plus r squared. That's the distance between them, and it's the distance between them squared. Right, so let's make sure we understand that. So the distance, so we're just talking about the force of plus little q on big Q, and the distance between them is the hypotenuse of this triangle, which has one side of d over 2 and the other side is r by what I told you in the beginning. And so the hypotenuse is the square root of d over 2 squared plus r squared, right? That's Pythagorean theorem. And so the force between them is KQQ over the distance between them squared. I won't say r because r is a different quantity here. Okay. So that is the magnitude of the force. And what's the direction of the force? Assuming that both of these charges are positive by the problem given, the direction of the force is in that direction. Okay. So we can call it in the r hat direction of plus q, right? Plus q to minus q. Whatever you want to call that direction, r hat. So r hat plus q. What about the other one? The minus q. The minus q, so we can now find what is the force of the minus q on q. Well, the force, we're talking about, I'm going to change my highlighter color. Let's change it to a green. Oops, wait, sorry. Oh my. We're talking about the force of this one on this one. All right, so they have a distance between them, which is the same as the distance between the other two. And so the force is K minus Q, big Q, divided by the distance between them squared. D over 2 squared plus R squared, square rooted, squared, distance between them squared. And that is in what direction? What direction is it? Because minus Q is a negative charge, that's what the minus sign indicates, this should be an attractive force. So the direction of that force is towards minus Q. So it's in the minus r hat direction. It's towards, that's what minus r hat means. R hat means away from, minus r hat means towards. So the direction is that. These two directions don't really matter because in a second we're just gonna see how we can ignore them. So the two directions are drawn in purple on the diagram. So the sum of those two vectors, notice that these two vectors have the same magnitude, they're just in different directions. So ignoring all the minus signs, they've got the same magnitude. They're just in different directions, and it's symmetric so that the force due to the plus Q, let me draw a new picture. So these are my two forces on big Q. What I can do is look at their components. Let's look at the components of the force on minus Q. It's got a component in the horizontal direction and a component in the vertical direction. And then the other one also has a component in the horizontal direction and a component in the opposite vertical direction. When you add those two vectors, because they've got the same magnitude and it's symmetric, so therefore they've got the same angle, these two force components cancel. The up-down force components cancel, and only the sideways force components add. So if we call this the plus x direction, then the net force must be in the plus x direction. It's just the sum of the two horizontal components. So the net force is, I'm going to try to draw it again. But anyway, it's the sum of those two red vectors that are in the plus x direction. So in order to figure out what the net force is, we got to find those components. So I need to take one of these force triangles and figure out the components. And once I figure out the components of one of the force triangles, the other components are the same. So for example, this, which is F due to minus Q on Q, this component, the X component, is going to be F times the cosine of theta, where this is theta. Ah, but what's theta? Theta is at the picture. I'm going to draw something on top of the picture. Let's look at this line, the hypotenuse, and this line here. This is angle theta. This also is angle theta. That's the complementary angles or the z angles. There's different ways of putting it, but that's angle theta. So the angle theta that gives us the x component of the force is the same as the angle theta in the triangle that is made up of one side, which is d over 2, and the other side, which is r. So this is theta, so that the tangent of theta, because tangent is opposite over adjacent, is equal to r over adjacent, which is d over 2. Because remember, between the two charges is d, and we're looking at a triangle which takes only half of that distance, right? So this is d over 2. So tan theta is r over d over 2. Well, actually, I just realized, while that is true, notice that the component is written in terms of cosine theta. So rather than doing tan theta, let's do cosine theta for that triangle. Cosine of theta is, so katoa, adjacent, d over 2, divided by hypotenuse. The hypotenuse, remember, is, we already figured it out, is d over 2 squared plus r squared. So that's what cosine theta is. So therefore, f cosine theta, I'm going to copy f from the other page, kqq over the square root of the hypotenuse squared. So this is f, k, this is the magnitude of f, right? K, q, q, little q, big Q, over d over 2 squared plus r squared. That square root squared, the square root squared goes away. That is the magnitude of f, and cosine theta is d over 2 over square root of d over 2 squared plus r squared. I mean, it's a little bit of algebra, but it's not hard algebra. So just make sure you understand that this is the magnitude of the force and this is cosine theta. And that is the component for one of them. It's actually the component for both of them. So therefore the net force, right? Because remember, the two components, whoops, where'd it go? I guess I don't have a good picture of it anymore because I drew on top of the picture, but both x components are the same. So this is the x component. This is the x component of both forces. It's the absolute value of that. It's just a positive quantity. They're both pointed in the plus x direction. So therefore, the net force is equal to 2 times the x component of any one of the forces, which is 2 times that. There you go. I just wrote it down again, multiplied by 2. We could actually simplify this. I'm going to simplify it. Go ahead and simplify that algebra. So this is the magnitude of the net force due to the dipole on big Q, and the direction is just in the x hat direction. There you go. That's the net force due to the dipole. At that point. That's an easy point to do. If I had chosen something that was off axis, right, off that central axis, if I had asked what is the net force due to the dipole at sort of a point over here, if I put big Q over here, then it would be asymmetric and we wouldn't be able to do this, right? We wouldn't be able to just simply say that the net force is just 2 times the x component. The reason why the net force is 2 times the x component is because it's a symmetrical problem. But if I go off axis, it's not symmetrical anymore, and it's just a slightly harder thing to do. But we just have to find the radius, the radius vector there and the radius vector there, and we'd have to add these two forces. Whoops, one would be in this direction. Anyway, doing that problem. So that's the force. Now, what about the field? What is the field of the dipole? Well, this is actually not a very hard question. Field of the dipole, if the two charges are separated by a distance d, what is the field at a distance r away from their centers? The field is simply the net electric force divided by, and we just divide out the charge that was there. We take away big Q, divide out the charge, and it is a vector. The field is KQQD over blah, blah, blah. KQQD over D over 2 squared plus R squared. Make sure I got that right. To the 3 halves. X hat. But I didn't divide out Q. So that was the force, but divide out the Q, and there you go. KQD over that. And that's the field. So what's the direction of the field at that point? The direction of the field at that point is this direction. That's the direction of the field at that point. So now let's go off axis and ask, well, what's the direction of the field, let's say, at this point? Let me just redraw the picture. Just made it a little less crowded. We figured out the direction of the field at that point is to the right. What's the direction of the field at, say, here, let's just go over here. Let's say this point. Well, notice that this point is closer to plus Q. So the field due to plus Q would be like that. The field due to minus Q would be like that. Right? So because we're farther from the minus Q than the plus Q, so it's asymmetric. And we'd have to add those two, so the net field maybe is sort of in that direction. So that would be, well, it would be longer than that, but anyway. It would be sort of like that. So that's the field at that point. And what's the field at this point? Well, it's going to point more towards the minus Q. And you could go ahead and just say, well, that's because the field due to the plus Q would be like this. The field due to the minus Q would be a larger vector like that. When you add them, you get the black vector. Okay, so we can do that everywhere. And what you find... What if I asked, what is the field, for example, over here? Over here, the field due to the plus Q, again, we just sum them up. The field due to the plus Q is going to be in that direction. The field due to the minus Q is going to be in that direction. The field due to the minus Q is smaller because we're farther away from the minus Q than the plus Q. So the net field is in that direction. And the same thing on this side of the minus Q, the net field's in that direction. What you end up getting for a field map is that the field lines go out like that, they come in like that, but if we move off of that central axis, like move a little over here, the field line sort of points, well, basically what you get is this. That's what I was trying to show with these in here, is that you get something like this. You get something like this. So if you were to try to figure out everywhere what the field looks like, the field is going to look something like what I've drawn here. And then on top, we got the same thing. It's symmetric, right? That the field lines go away from the plus, but they come into the minus. The field of a dipole. This is what a dipole field looks like. You can see that out here, the lines are farther apart, so the field is weaker. In here, the lines are closer together, so the field is stronger. You can see that the field originates on plus charges and terminates on minus charges, and that none of the field lines ever cross. So that's the electric field due to dipole. So what we're going to do is we're going to start looking at electric fields due to collections of charges, and in particular, we'll stick with pretty symmetric situations. So we've got point charges and spheres of charges. Spheres look the same as points. So if a point charge has a certain field, then at least outside of it, a sphere of charge is going to have the same field, right? So the sphere of charge still has a field that looks like a point outside of it. Later on, we got to talk about what it looks like inside of it. And then we'll talk about line. We got dipoles, which we talked about. We'll talk about line of charge. What if I have a bunch of charges in a line, let's say a continuous line, right? Let's just say plus, 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 plus. Each of those positive charges, you got to imagine what happens at any point. Each of those positive charges has a field that points away like this at each of those points. And if this is a symmetric situation, let's say it's a really long line of charges or an infinitely long line of charges, or we're at the center of a line of charges, all of the horizontal components cancel and all of the vertical components add, right? If we add up all of the field lines, if ask what is the field here due to all these pluses, what we're going to do is we're going to simply get field lines that point away from this and away from the line, and all those are going to add. Imagine all the horizontal components cancel and all the vertical components add so that the net field at that point is in that direction. And actually, this is going to be the case for a line of charge, is that the field will point away from the line. But this is in 3 dimensions, so we have to think cylindrically. So look at the end of the line of charge, right? If this is a line of charge going into the page, right? So if we're looking at it from this end, and that's the view we're getting here, the field is going to point away from the line of charge. Looks sort of like the field of a point, except for the fact that it's got cylindrical symmetry, right? So in 3 dimensions, maybe we think of it like this. In 3 dimensions, the field points cylindrically away from a line of charge. So a line of charge is one symmetry we're going to consider. A point charge, a dipole, and then spheres of charge, and then sheet of charge, a sheet of charge. And that's really where I want to go next, is to think about what kind of field does a sheet of charge have. We'll pick that up later.